There are tests we cannot perform here because we do not have the necessary instruments. But there is a crucial test, which is the performance of the internal voltage regulator. Now I will show you a video about it. To describe the voltage variation test, first we should keep in mind that the transmitter has an internal voltage regulator. What this means is that regardless of the voltage that circulates through the network, this allows the plant to adapt and work by itself. One must always take into consideration the following principle, which is, if the transmitter supplies 3,500 watts and remains stable, it does not matter that the input voltage varies, because the current consumed is proportional to the voltage of the feeding line. Let's explain a little. If the plant is supplying 3,500 watts and it consumes 5,000 watts, the outcome of the voltage current should always be kept in 5,000. Based on this, we can say that if 23 amps are consumed with 220 volts with a lower voltage, say 200, 30 amps would be consumed. If the voltage is decreased even more, say to 180, the amps will increase to 35 or 40, but they will go down to 20 amps if the voltage rises to 240. Sure enough, the transmitter tries to keep the output power constant, but there is a limit. Let's think about how this is in reality. We start with 200 volts. In this case, it is much lower than that, and that is why we have 30 amps. If it continues decreasing, there comes a moment where the cable may be burned, or the fuses that are on top. As you can see, the plant keeps working regardless of the voltage it is supplied. However, if the transmitter detects a considerable variation that could cause serious problems, it will launch its security measures. So, this ELENOS equipment we are showing is called variant. It is called like that because it has the capacity to independently vary the voltage of each phase. And you will be able to determine the voltage being supplied through these instruments. For example, here we can see the current each phase consumes. This feature is present in all ELENOS transmitters. Also, you can see how they behaved in each test on the test sheets supplied at the end of the manual we gave you. For example, one of the tests you will find on the manual is what happens in the plant when we set the incoming voltage at 250 volts. Why do we make this test? Because we need to be sure the transmitter will not be damaged if a peak occurs. It is clear that 400 or 300 volts cannot be provided, but if we supply 250, we are sure it will not be damaged because it passed this test perfectly in the factory, just like we are doing right now. If we pay attention to the parameters, we can confirm that all measures are within normal range. The plant did not modify any value, and the only thing that happened is there was a decrease in the absorption current. As you can see, it went from 23 to 20 amps, but the machine keeps working as it should. As I was saying, we supply 250 volts and leave it working for a while. In the meantime, we will take some audio measures and of other parameters around the transmitter. This will give it some time, after which we will proceed to evaluate what will happen if the incoming voltage is reduced. Occasionally, this is as dangerous as when it increases. Why? Because, as we said earlier, when the incoming voltage is reduced, the current increases considerably, and some transmitters are damaged because the source is designed to work perfectly at 220 or 250 volts. But at 190, there is a peak of current of such magnitude that it can damage a small transformer or a MOSFET. It should be taken into consideration that right now at 200 volts and at approximately 30 amps, 40 or 50 amps can be reached if the voltage decreases to 190. But even if this happens, we guarantee that the transmitter will work without any problems. We can see now that the wattmeter indicates 3,500 watts. The plant went from 250 to 190 volts, and in spite of that, it kept working normally. What could possibly happen is that the transmitter keeps varying, keeps going down and reaches 150 volts, like in this case. At this point, it is best to prevent because the current consumed at 150 volts is so high that we risk damaging a fuse or a power source. Here we can perfectly see how the output power decreased. And just as it occurred on the other cases when the output power decreased, the current in all MOSFETs and the input voltage decreased as well. This is why the transmitter starts a protection phase. That is to say, it consumes less current, preventing a possible irreparable damage to a fuse, which would cause the plant to stop. When continuing the test, we will notice that if the voltage keeps decreasing, a time will come when the transmitter stops. Let's decrease the voltage even more. Let's take it to 120 volts and notice that the output power also decreases very much, causing the alarms to go off. This makes the plant protect itself. Despite the power reduction, the transmitter keeps working. But if we insist on reducing the power, on decreasing the voltage, the equipment will sooner or later stop working. What happened during this entire process? We proved that between 250 and 190 volts, the transmitter worked perfectly. As the voltage decreased, the power diminished until it stopped. But when the plant recovers its ideal voltage, it goes back to its initial activity. Note how it is now supplying its normal power. The MOSFETs are stable and the voltage of the feeders is stable as well. In other words, the equipment will always recover after a problem, in this case, for instance, a voltage variation. The other test we performed is to investigate what would happen if we removed a source. Although we already did this when we turned the source off from here, but we truly performed this test in the factory by extracting a phase. This way, the test is but more rigorous since it is a situation that could happen in real life at any given moment in a radio station. We turned it off to simulate the lack of a phase, but when we eliminate it, the output power also decreases just as we saw here. There is an additional test that seems simple, but it's not. We caused several network interruptions in all transmitters, an event that usually deteriorates the plant. Usually when the power goes off, it does it in a violent way, and the plant does not suffer. But when it comes back, it does it intermittently. It comes and goes, generating peaks of tension, which is what evidently damages the transmitter. But this is not a cause of concern, because regardless of the voltage variation, as long as it doesn't go over 260 volts, we guarantee the equipment will not be damaged. Sponsored by 305 Broadcast. Voiceover by Audio Studio.